In this video, I'm going to be developing the curvature formulas in calculus. I'm going to be showing you why these formulas are working. So to start with, I'm going to remind you of the definition of curvature of a parametrized curve. Okay, kappa, the letter we use to denote curvature, it's the length of t prime of s, where s is the arc length parameter. Okay, so if you had your curve parameterized with respect to arc length and you found the unit tangent in that parameterization and took the derivative of it and found the length of that, that would give you the curvature. But in practice, this is not really realistic. We're not going to be reparameterizing with respect to arc length very frequently. We need better formulas. So that's where these things come in. And I think I probably showed you this in class. Here's a bunch of formulas that happen to work for curvature. And of course, in class, we don't have time to prove them for you. But here, I'm going to prove them for you right now. And I'm just going to kind of go in the order that they're presented. First, I'm going to show you why the length of t prime over the length of r prime works. Then I'm going to show you why the formula with the cross product works. Then I'm going to use that cross product formula to develop the formula that you're using for a plane curve or for y equals f of x. All right, so let's start with curvature equals length of t prime divided by length of r prime. So the definition of curvature is the length of dt ds, and so that's kind of related to t prime. So let's start with t prime, the idea of t prime, and that's going to be the derivative of the unit tangent vector with respect to time, our kind of natural parameterization, or really whatever parameterization we have that is not the arc length parameterization. Okay, I'm going to think about this in terms of the chain rule, though. Because I'm going to think about, okay, the arc length parameterization, it exists, it's out there. I might not want to work with it, but, it's there. Okay, I could write this equivalently as dt ds times ds dt, with the chain rule. And then this is going to be something I can work with, right? Because that dt ds, that's close to the meaning of curvature. Okay, if I took the length of that vector, that would give me the curvature. So I'm going to do a little bit of algebra here. But first I'm going to also notice that ds dt is the length of r prime. Okay, and if you need a little bit more on that, go back and watch the video on reparameterization with respect to arc length, and I bet you can kind of click up at the top, and it will take you back there. Okay, but now I'm going to do the algebra, right? Having replaced ds dt with r prime, I think. So t prime, no, yeah. First, I'm going to replace ds dt with r prime, and then I'm going to solve for dt ds by dividing by r prime. So now dt ds is equal to t prime over the length of r prime, and we're pretty close to there, right? Because this looks close to the formula we're trying to show. Okay, what we're going to do, we're going to consider the length of dt ds, because that's really what curvature is. Okay, we're going to take the length of that vector, and if you think about it, I didn't really use the vector hats in the appropriate places, and I'll go back and clean that up here in a second. But t prime is a vector, and the length of r prime is just a constant. So if I'm taking the length of that vector, that's just a vector divided by the constant, that would be equivalent to just taking the length of the vector and dividing it by that constant. Okay? And then also noticing that the length of dt ds, well, that's the definition of curvature. Alright, so that's why the length of t prime over the length of r prime works, is it's really because of the chain rule. Alright, now let's do the curvature formula that has the cross product in it. And this one's probably going to be the most labor intensive to show, but it's going to be well worth it because it really makes the other two formulas very easy to demonstrate. So I'm going to start off by reminding you about the definition of t and then also ds dt. So t is r prime divided by the length of r prime, is the unit vector in the direction of the derivative. And ds dt is equal to the length of r prime, which is also something that I showed you most recently in the reparameterization with respect to arc length video. So now I'm going to solve for r prime out of that first formula where, in terms of the length of r prime and t. I'm going to multiply both sides of that equation by the length of r prime. And so I'll say r prime equals the length of r prime multiplied by t. And now I'm also going to need r double prime if I want to cross those two things. Okay, but first I'm going to also, I'm going to point out that length of r prime, that's ds dt, and that's going to be a little bit easier for us to work with when we're going over here to take derivatives. Okay, now I will point out that both ds dt and the unit tangent vector, these things are going to depend on the time parameter, the lowercase t. So when I take the derivative of r prime, I'm going to need to observe the product rule. So r double prime is going to be, first I'll take the derivative of ds dt with respect to t, and I'll get the second derivative of s with respect to t both times, and I'll leave the unit tangent vector the same, and then I'll add, leaving ds dt the same, the derivative of the unit tangent vector. Okay, so now that I've got r prime and r double prime, I'm going to be interested in crossing them. And you might be worried because it's like, I don't have any of the components of these things. How am I going to do a cross product if I don't have any of the components? And I guess I would say carefully, like using properties of cross products. Now, this is something that we definitely have not talked about in multivariable calculus. If you're with me in linear algebra, we may have briefly run into this property before. But the cross product does distribute over addition. And so I've got r prime, which is ds dt multiplied by the unit tangent vector, crossed with r double prime, which is the sum there that I got from the product rule. And so I'm going to do the distribution. Okay, I'm going to say that first I'm going to have the, first, the ds dt times the unit tangent vector times the one with the second derivative. Okay, and so I'll have those two things times t crossed with t. Okay, and I'll hopefully, maybe you remember what happens if you cross a vector with itself from linear algebra, but if not, I'll remind you. And then there's the other one where we're going to have 2 powers of ds dt multiplied by unit tangent crossed with the derivative of the unit tangent. Okay, so I'm going to remind you that if we cross a vector with itself, we're going to get the zero vector. And just think about how you take a cross product. Set one up where they're both exactly the same, and then you'll realize, okay, when I'm going to do those determinants, I'm going to get 0 every time. Okay, also the unit tangent vector, capital T, it's a unit vector always, so its length is always 1. And I showed you recently that if you've got a vector valued function with a constant length, it is always orthogonal to its derivative. And that fact will be useful to us here. So I'm going to go back to this cross product formula and say, okay, now I'm going to, apply the fact that vector crossed with itself is the 0 vector. So that first term is going to go 0 because t crossed with t is 0. So now I just have 2 powers of ds dt along with t unit tangent vector crossed with its derivative. Okay. But what I'm really interested in is not really the cross product, but the length of the cross product. If you look at the very top in blue, what I'm trying to show. So I'm going to take the length of this cross product and use that sign property, where the length of the cross product is the length of each of the factors of the product multiplied by the sine of the angle in between them. And if I've got this constant multiplier out front, which is the ds dt squared, well, that's just still going to be out front. That's another property of cross products I'm not going to get into right now. But if they're orthogonal, then the angle between them is pi over 2, and sine of pi over 2 is 1, so this is going pretty well. Okay, I'm going to say that it's going to be ds dt squared times the length of the unit tangent vector. Well, I already know that that's 1, times the length of the derivative of the unit tangent vector, which I don't know what that is. But so I've kind of got it whittled down a little bit. Okay. Now, I'm going to solve for the length of t prime. Okay. Because I'm going to equate this to the length of t prime over the length of r prime, which I just previously showed was equivalent to the curvature. So if I solve for the length of t prime, I'm going to basically divide both sides of the equation by ds dt squared. And then I'm going to apply the other formula that's up at the top in yellow highlighter written in black, that ds dt is the length of r prime. So that'll mean I have 2 powers of the length of r prime. But what I'm really looking for to get curvature is the length of t prime over the length of r prime. So I'm going to divide both sides of this equation by another factor of r, or the length of r prime, and that's going to give me that curvature. And so that's where I'll get the one that has the length of r cubed. Okay. So you might have been thinking it's kind of a little unnatural to have like the third power of the length, but that's why we've got that there. And so if we've got this property shown, then the next two will be much easier. All right, now I'm going to show you about this formula that works for a plane curve, for a parametrized curve in two-dimensional space. Okay, what we're going to do is we're going to parameterize this with x of t, y of t, and then we're going to let z of t equal 0. Okay, and then we're going to use the cross product formula. So let r of t equal x, y, and 0. We're going to need the derivative of r, and we're also going to need the derivative of r. So r prime will equal x prime, y prime, and 0, and r double prime will equal x double prime, y double prime, and 0. Now we're going to set up to cross r prime and r double prime. So we kind of write out the matrix we want the determinant of, set up our little structure. Look, notice that the first two determinants are both going to be 0. And then the last one, when I cover up the column that has the k in it, I'm going to get x prime y double prime minus y prime x double prime. Okay, and to write that out as vector, I'm going to say it's 0, 0, and x prime y double prime minus y prime x double prime. So this is promising, right? You see that that's kind of the numerator. If I take the length of r prime crossed with r double prime, well, the length of a vector that has 0, 0, and some other number is going to be just that other number. Maybe the absolute value of it, though, right? If I think about squaring it and then taking the square root, if it had been negative, I'd kind of lose that negativity. So the length of r prime crossed with r double prime is going to be the absolute value of x prime y double prime minus y prime x double prime. And so I just need to show the denominator, so I bet that that ends up being the length of r prime cubed. But let's find the length of r prime. Okay? That would be the square root of x prime squared plus y prime squared. But maybe for the sake of making it match with the formula, rather than calling it the square root, I'll call it the 1/2 power. Okay, and so that when I go and put these pieces together to use the formula for curvature that I just previously showed you with the cross product, I'm going to take the cross product, I'm going to divide it by the length of r prime to the third power, and that's where I'm going to get that 3/2 power. Okay, and the last formula I've got for you is if you've got y equals f of x, and this is not one that I use in my multivariable calculus class because it's a multivariable calculus class, and y equals f of x is a patently single variable situation. But it's a formula that really doesn't come up in that many single variable calculus classes, I think mostly because it's not part of AP calculus. But we're going to start off by parametrizing y equals f of x with x equals t, y equals f of t, and z equals 0. Okay. And so I'll have r of t equaling t, f of t, and 0. So I'm going to need r prime and r double prime. So r prime will be 1, f prime, and 0, and r double prime will be 0, f double prime, and 0. Just like with the other formula, I'm going to set up the cross product of r prime and r double prime. And notice that the first two determinants are going to come back 0. And then the third determinant will just be f double prime. Okay, and so I'll write it as a vector, and again, if I'm taking the length of that vector, it's just going to be the absolute value of f double prime. So I've got the length of the cross product equals the absolute value of f double prime, and again, this is looking pretty promising. I'm going to go for the length of r prime, and that's going to give me 1 plus f prime squared, right? 1 squared plus f prime squared plus 0 squared, square rooted, I'll write as the 1/2 power so that it makes sense with the formula, and then go to apply kappa equals the cross product of r prime and r double prime divided by the length of r prime cubed, and that's where I'll get the absolute value of f double prime of x divided by 1 plus f prime of x squared to the 3/2 power. And so that's all four of the curvature formulas that we use in my calculus class. This is the proof of all of them. This is why all of them work. So that's going to be all for this video. Thanks for watching.